Good morning. Welcome to the class. Today we start the 4th week of classes, and the topic of this week will be probability and Bayes learning. Before we proceed to Bayesian learning, I will like to talk about the basics of probability for you to be able to properly understand this portion of the class and some later portions. So, many of you may be familiar with probability. Probability is the study of randomness and uncertainty. Many of the times there is a lot of uncertainty in the world and we cannot predict exactly what will be happening, and probability is a framework for representing uncertainty and dealing with uncertainty and randomness. So, we will look at certain definitions pertaining to this study of uncertainty. First of all, let us look at what is a random experiment. So, random experiment is a process whose outcome is uncertain. Its outcome is not fixed, its outcome is uncertain. For example, let us take some examples. Suppose you toss a coin. What are the possible outcomes? Outcomes may be head or tail. These are the two possible outcomes, and it may be head, it may be tail. Suppose you toss 10 coins and you look at the number of tosses, number of coins which turned up head. This number can be 0 or 1 or 2 or up to 10. So, there are 11 possible values and they have different probabilities of occurring. So, this uncertainty is there in a random experiment. Or you could think of another experiment where you toss a coin repeatedly until you get a head. So, you can get a head in the first coin itself, or after 5 tosses or 7 tosses or 17 tosses. So, the outcome of the experiment can be 1, 2, 3, 4, any number, any natural number, and with different probabilities. So, this is another experiment. Later we will see we can define a random variable as related to the outcome of an experiment. Okay. So, next we talk about events and sample spaces. So, sample space denoted by omega. So, what is a sample space? I think it will be clear if you look at these slides. So, these red dots are the different possible outcomes of a random experiment. There is a random experiment, these red dots are the possible outcomes, and the set of all possible outcomes is called the sample space. So, in this slide, all the red dots together, the union of those correspond to the sample space. If you look at a single dot, that is a single event or a simple event, which are the individual outcomes, and you can have a set of an event to be a collection of one or more simple events. So, if you look at this inner shape, these 1, 2, 3, 4, 5, 6, these 6 possible outcomes define an event. This event is a collection of simple events. So, events may be simple or events may consist of a number of simple events, and we can say an event is a subset of the sample space. Okay. So, number 3, we need to define and understand what an event is. So, more formally, we can say a sample space omega is a set of all possible outcomes of an experiment. And an event to be a subset of the sample space. Suppose your experiment is to roll a die or roll a dice. What are the possible outcomes? 1, 2, 3, 4, 5, 6. Suppose your experiment is rolling 2 dices and taking the sum of the values on each dice. So, what are the possible values of this outcomes of this event? It can be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Suppose your event is tossing 3 coins. What are the possible results of these 3 coin tosses? They can all be head, 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 tail, head, tail, head, head, tail, tail. Like this, there are 8 possible outcomes. So, this is what we mean by a sample space. And events, as I said, is the subset of the sample space. Suppose we want to take that when you toss a coin, you want to look at what is the probability that the let us look, say you are tossing a die, what is the probability that the result is even. So, a die has 6 possible outcomes, 1, 2, 3, 4, 5, 6. If it is 2 or 4 or 6, we say that the outcome is even, and we can say that this is a possible event. You could toss 3 heads and find out define an event to be when there are at least 2 heads. So, the possible events can be head, head, tail, tail, head, 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 tail, head, 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 head. Out of 8 possible outcomes, these 4 possible outcomes denote where the 2 heads are there, and this can define an event. So, event is a subset of the sample space. The second thing, the third thing that we need in order to define a probability space, we require to have a sample space, we require to know what is the event, and fourthly, we have to define the probability function. And this probability, what is probability? The probability is, first of all, let us look at certain properties of probability. Suppose probability is associated with an event. Suppose A is an event, and as we have seen that A is a subset of the sample space. So, A is an event which is the sample of, which is a subset of the sample space, and PA denotes the probability of this event A. So, what it means is that when this experiment takes place, you look at the outcome of the experiment and you find out what is the probability that the outcome of the event is in A. This is called probability of A. And we can define probability of A complement as this event not happening, and this will equal to 1 minus probability of A. Because if you consider that this is the sample space and A is your event, then A complement is omega minus A, and probability of A complement is 1 minus probability of A. If there are 2 events PA and PB, there are 2 events A and B are 2 events, then we can look at different probabilities associated with different combinations of the events. So, we can say probability of A union B. Now, in the case that B is disjoint from A, probability of A union B will be equal to PA plus PB if A, B are disjoint. However, A and B may not be disjoint. In that case, we may have that B is another subset of the sample space. A is a subset of the sample space, B is another subset of the sample space, and probability of A union B in the more general case will be PA plus PB minus probability of A intersection B. Because when you take probability of A, you are counting this region. When you are taking probability of B is also counting the same region. So, this region, the probability associated with this region, which is at the intersection of A and B, it gets counted twice. That is why you need to subtract this. I am assuming that all of you are familiar with basic set theory. Now, if you have three events A, B, C, similarly, you can figure out that this is equal to PA plus PB plus PC minus P A intersection B minus P B intersection C minus P A intersection C plus P A intersection B intersection C. So, by drawing the Venn diagram of the three events, you can easily derive this. So, a probability is a number which is assigned to each event in the sample space. A probability is a number assigned to each event in the sample space, and probability follows certain axioms. These numbers follow certain axioms. So, let me write down what are the basic axioms of probability. So, this is what we call axioms of probability. So, for any event A is any event, PA is greater than equal to 0 and less than equal to 1 for any event A. And omega is the sample space collection of all events. So, probability of omega will be, so always the outcome of the event will come from the sample space. So, probability of omega is 1. Probability of the null event is 0. Nothing happening, at least when you do the experiment, the result will be from the sample space, right. So, there is no possibility that nothing will be there. So, null event is no outcome happening, and that probability is 0. Also, if A1, A2, An, so if A1, A2, An, suppose they are disjoint events and their union is A. So, we say that A1, A2, A3, An form a partition of A. So, A is an event. Let me illustrate in this picture. Suppose A is an event and A is partitioned into 4 parts. This is A1, A2, A3, A4. So that they are pairwise, these events are disjoint. A1, A2, A3, A4 are pairwise disjoint, and the union of them is equal to A. In those cases, PA, probability of A, equal to probability of A1 plus probability of A2 plus probability of an. This is if the events are disjoint. If they are not disjoint, then we have to use formula which I had already illustrated for 2 and 3 events. Intuitively, the probability of an event can be looked upon as the number of times the outcome of the experiment is the event divided by the total number of experiments. So we can write that A is an event. We can write PA is number of times the event occurs divided by total number of experiments, and we can take the limit when n tends to infinity. If you have infinite number, if you carry on the experiment infinite number of times, you can look at the proportion of the experiments for which you get that event. Now, next what we will do is that we will come to the next definition, which is that of a random variable. Now, what is a random variable? This is something which many people get, the name of the term random variable is a misnomer, and people, try to think that random variable is a variable. But a random variable is a function defined on the sample space omega. Let me look at the slide so that we can do this quickly. So, random variable is a function defined on the sample space omega. So, it maps the outcome. So, suppose this is your omega, and it maps the outcome of a random event into real scalar values. Suppose small omega is an outcome, and the random variable is a function which associates with any of these outcomes a function. Let us say that function is x of omega. Right? So, this is a random variable. And for example, let us say that you toss 2 dices, you roll 2 dices, and you look at the sum of the values on the 2 dices. So, this is the experiment, and for one particular event, for one particular this thing, you may get 2 on one dice, 3 on another dice. So, the outcome is 2 plus 3, 5. So, a random variable maps an event to a real value. So, the random variables may take on only a countable number of distinct values. For example, the sum of the value of 2 dices, as I had said. We say that x is a random variable. It's a convention to denote a random variable by a capital letter. X is a random variable with arity k if it can take on exactly 1 out of k values. For example, associated with the random variable, the sum of the values of 2 dices, the possible outcomes are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, once we have defined random variable, let us look at what we mean by the probability of a random variable. Now, random variables may be discrete or continuous. First, we will talk about discrete random variables. The probability mass function of a discrete random variable, suppose capital X is a discrete random variable, and let us say capital X takes value small x1, small x2, small xn, where x1, x2, xn are discrete values. Now, we can associate a probability mass function with this random variable taking one value within this range. So associated with this we can have a probability. Similarly, we have probability associated with capital X equal to small x1, capital X equal to small x2, capital X equal to small xn, and these values that define the probability mass function. So probability mass function denoted by PMF is the probability that this random variable capital X takes values x1, takes values x2, takes values xn. Okay, and these are all the values that it can take. So sum of probability x equal to x1 plus probability x equal to x2 dot 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 plus probability x equal to xn will be 1, because capital X will take one of these values. Associated with each one of them there is a probability, and probability mass function specifies all these probabilities. So the sum of these probabilities will be equal to 1. So sigma I equal to 1 to n probability of x equal to xi equal to 1 by the axiom of probability, which we have already studied, because x can take either x1 or x2 or x3 or xn. It cannot take two simultaneously. Okay, so if you look at the slide, so let's look at all these properties quickly. So as I have already said, sigma probability x equal to xi equal to 1, and probability x equal to xi intersection x equal to xj is 0 if I not equal to j, because the random variable capital X can only take one value. Secondly, probability of x equal to xi union probability capital X equal to xj is probability x equal to xi plus probability x equal to xj, because they are disjoint outcomes, and the union of all these events x taking each of these values is equal to 1. Now probability mass function is a distribution of a discrete random variable, and this distribution can be arbitrary. There are standard distributions people study, and we will look at some standard distribution. So x varies as u1 to n. U stands for uniform distribution. If we say that x is a random variable which is uniformly distributed between 1 and n, what we mean is that x can take value 1, 2, 3, 4, n, etc., and probability that x equal to small I, where I is an integer between 1 and n, is equal to 1 by capital N. Okay. For any I, probability of x equal to, for any I in this range, probability of x equal to I is 1 by n. Similarly, another common distribution is the binomial distribution, and the binomial distribution has two parameters n and p. And if you look at the slide, in the binomial distribution, x takes values of 0, 1, 2, 4, n, and probability that capital X equal to I, small I, is given by nci p to the power I 1 minus p to the power n minus I. When you flip n coins, the number of the probability of there being I heads can be given by this binomial distribution. This is a common random distribution. Next, we briefly talk about what is joint distribution. If you have two random variables x and y, the joint distribution is the distribution of x and y together. So suppose x takes values x1, x2, xn, y takes values y1, y2, yn. So probability that x equal to small xi, y equal to small yj for xi between x1 and xn, yj between y1 and ym. This particular distribution specifies the joint distribution of two random variables. Suppose you toss 10 coins, your friend tosses 10 coins, and you get I heads and your friend gets j head. This can be represented by a joint distribution. The next what we discuss is conditional probability. So, conditional probability is, suppose you have two random variables, capital X and capital Y. Probability that capital X takes value small x, given that capital Y gets value small y, is the probability of x equal to x given the occurrence of y equal to y. Suppose we can say that probability of you getting 0 heads given that your friend gets 5 heads. This can be represented by the conditional probability. The law of total probability. If you are given two random variables x and y, which take values in this range x1 to xm and y1 to yn, probability x equal to xi is summation over all possible j's, probability of x equal to xi and y equal to yj. When you want to find probability of x equal to xi and you have the joint distribution of x and y, you can sum over the probabilities of xi and yj for all yj's. So, this is called marginalization, which is given by probability of x equal to x. So, this probability x equal to xi and y equal to yj is given by the conditional probability x equal to xi given y equal to yj and times probability y equal to yj. And this operation that we performed is called marginalization. When you have a joint distribution and you are interested in a subset of the random variables, not all the random variables in the joint distribution, you can take the summation over the values of those variables which you are not interested in, and this process is called marginalization. Now, we come to a very important rule called Bayes rule. So, Bayes rule is very important in Bayesian learning, in learning that, as we will see. Suppose x and y are discrete random variables, then this conditional distribution probability, let me first write it in a simple way. Bayes rule. Suppose x and y are two random variables. Probability x given y can be written as probability y given x times probability of x divided by probability of y, which means that if you take small x to be the value of the random variable capital X, small y to be the value of random variable capital Y, probability that x equal to x given y equal to y is probability of x equal to x and y equal to y, which is probability of y equal to yi given x equal to xi times probability x equal to xi and divided by probability of y equal to 1. Now, in order to find out probability of y equal to small y, you can marginalize over all possible values of the random variable x, and this is what happens here. In this denominator, we are doing the marginalization, and this is Bayes rule. Okay? And Bayes rule can be defined from the chain rule of probability. You see, we have earlier saw that if we write it in a simpler notation, probability of x y equal to probability of x times probability of y given x. Similarly, we can write probability of x y is same as probability of y x, which is probability of y times probability x given y. Now, if you combine the right hand side of these two equations, you will get this Bayes rule, and Bayes rule plays a very important part in machine learning. Now x and y are two random variables. We say that they are independent if x equal to the outcome of x, the value of x does not affect the probability of y equal to y. So if x and y are independent, then probability of x y is probability of x times probability of y. But if they are not independent, then this chain rule will apply. Probability of x y equal to probability of x times probability of y given x. But if y is independent of x, probability of x y is px into py, as we see here. Okay, so more on independence. Probability of x equal to small x and y equal to small y equal to probability of x equal to small x times probability y equal to small y. And what is conditionally independent? So that is independent random variable. We can also have conditionally independent random variables, which we will require in our subsequent classes. We say x and y are two random variables, are conditionally independent given another random variable z. This means that once z is known, the value of x does not add any additional information about y. What is total independence? If value of x is completely independent of the value of y, then x and y are totally independent. But there is a restricted case. We say that if z is known, then value of x does not affect the value of y. This is called conditional probability. This means that if the value of z is not known, then x and y may not be independent. Okay. So more formally, we say x and y are conditionally independent given z if and only if probability of x y given z equal to probability x given z times probability y given z. So in a shorthand, we can write conditional independence means probability of x y given z equal to probability of x given z times probability of y given z. Next, we will briefly talk about what is continuous random variable. Discrete random variable takes one of a countable set of values. A continuous variable takes continuous values. If x is continuous, we use probability density function instead of probability mass function. In the probability density function, which is called PDF of a continuous random variable, is given by fx, where x is any point in the range of the small x is any point in the range of random variable capital X, and small fx describes the probability density in terms of the input variable x. So properties of a probability density function: for any x, fx is greater than equal to 0, and summation of minus infinity to plus infinity fx equal to 1. This is the laws of the probability, axiom of probability in the continuous space, and fx has to be less than equal to 1. The actual probability can be obtained by taking the integral of PDF, because we have points. At each point the probability can be very small. So we can look at probability of within a range. Probability that x takes value within the range 0 to 1 is given by this definite integration of 0 to 1 fx dx. This gives the probability in this range. And we have cumulative density. So PDF is the probability density function, and we can also have cumulative distribution function, which is denoted by capital F. Capital F, the cumulative distribution function of random variable x at nu, is given by probability that x less than equal to nu. For discrete random variables also we can define cumulative distribution. For continuous random variable, the cumulative distribution is given by the integration from minus infinity to nu fx dx. And we can see that this relation holds. D dx of the cumulative distribution of x is the point probability density function of x. So, cumulative density function is the summation of the previous densities up to that point, and by differentiating this cumulative distribution function, you can get the probability density function at a point. We will end by looking at one common distribution of continuous random variable. So, we say that the random variable x follows a normal distribution with parameters mu and sigma square if fx is given by this formula. For x in real numbers, fx is given by this formula, 1 by root over 2 pi into sigma exponential of minus x minus mu whole square divided by 2 sigma square. And this distribution is a very popular distribution. We may need to refer to it sometimes, and this picture shows you the shape of this distribution function. So, we have the function peaks at mu, where it has maximum value, mu is also the mean, and the function drops off on the right hand side or on the left hand side, and it continues up to infinity, but as the limit it goes to minus infinity or plus infinity, the value of this density function becomes 0. So, this is the normal distribution or Gaussian distribution, which is very popularly used in machine learning, because many processes in real life follow this distribution. And lastly, we talk about multivariate normal distribution. What we saw earlier was a distribution over a single variable, but in the other studies that we have seen, that in machine learning we deal with multiple features or multiple variables, and if we have multiple variables, we can have multivariate normal distribution. X1, x2, xd are multiple values of, so x is a vector of several features, and capital X1 takes value small x1, capital Xd takes value small xd, and the multivariate normal distribution is given by this formula. So, it is a multivariate distribution. It is difficult to visualize. Think of, we have two distributions x1 and x2. It is a hill which is bell shaped, and it has a footprint. If you take a cross section, it will be ellipsoidal, and we have, this is the formula for a multivariate normal distribution, and perhaps you could have seen a picture. Lastly, very last, what is mean and variance? The mean or expectation of a random variable is the average value of the random variable. For discrete random variables, the expectation of x is given by sigma over nu I, where nu I are the different values of the random variable, nu I times probability x equal to nu I. And for continuous random variable, it is summation integral of minus infinity to infinity x fx dx. Variance of x is expectation of x minus mu whole square. It measures how spread the function is, how wide the function is. For discrete random variables, Vx is given by summation over V nu I minus mu whole square times probability x equal to nu I, and for continuous random variables, it is given by integration minus infinity to plus infinity x minus mu whole square fx dx. And if you are given some samples, so you have the training set where you have for different experiments, different experiment is performed several times, and you get the values of these experiments. From those samples, you can compute an estimation of the mean as 1 by n sigma of xi. Similarly, you can estimate variance from the sample using this formula, sigma square equal to 1 by capital N minus 1 summation xi minus mu whole square. So, you can estimate mean and variance from the sample. This is called maximum likelihood estimation. We will not go into the details, but this will be useful in your subsequent classes. With this, we come to end of this lecture. Thank you.